connected to an infinite bus, our infinite bus, to a purely reactive circuit. So this circuit is assumed as a purely reactive circuit. That means there are no resistances in this circuit. Only we have reactance. As shown in the figure below, so this is our figure. So this figure is very familiar to us. This is the single line diagram of single machine infinite bus system. Reactances are marked on the figure on a common system base. That means the reactance values that are given here all are in common system base. That means all are given in per unitized value. So they are given in per unit. The generator is delivering real power PE. So the generator is delivering real power PE. That means this generator is actually delivering the PE. And Q, the reactive power, is 0.074 per unit to the infinite bus. That means this Q is delivered to the infinite bus. Okay. And this is supplied from the generator, and this is delivered to the QE. This is 0.074 per unit. This is actually delivered to the infinite bus voltage, and the infinite bus voltage is given as 1 per unit. That means this is the infinite bus voltage magnitude, and according to that, as we take this as a reference, the angle will be 0 degree. P is given here, but PV is here. Okay. But this circuit is assumed as a purely reactive circuit. Means that there are no resistances. Okay, so there will be no real power loss. Okay, means that actually this is a lossless system. So whatever P is supplying from the generator, the same P will be delivered here. Same. Okay, so the P will be same across this circuit, across this line. Okay. And the same P will come to this infinite bus. That will be the case. Okay. Now there are two parts, part A and part B. Actually, these two are for two different types of fault. In part A, the fault is near at the sending end, and in part B, the fault is away from the sending end. In part A, the temporary three-phase fault occurs at the sending end of the line at point F. So the point F is not mentioned here, but we can assume that this F is actually here, right? Because it is occurring at the sending end of the line. So the assumption is that when the fault is clear, both lines are intact. Okay. That means our before fault network and after fault network will be exactly same. With this assumption, we can understand that our after fault and before fault network are same. We have to determine the critical clearing angle, that is actually the delta T, the critical fault clearing time, that is this. We need to calculate this too. Okay. Then the part B. So first let's solve this part A, and then we can go to the part B. So part A is the temporary three-phase fault occurring at the sending end. That means this is right. The three-phase fault at one end of the transmission line. For this case, we had three scenarios: before fault, during fault, and after fault. Right? You know that the before fault and after fault network are exactly same. Due to this assumption that whenever the fault is clear, both lines are assumed to be clear. And during the fault, the power transfer to the infinite bus is actually zero. Yes, this is the during fault scenario. Now, then we calculated also the critical clearing angle, right? So this is the expression for solving the critical clearing angle delta C. Then also we calculated the expression of TC, the critical clearing time TC. Actually, we will apply these two equations. This equation to get delta C, and we will apply this equation to get the and these two reactions with only a single reactance, right? That will be called as the transfer reactance. So that will be the transfer reactance. Let's say this is X1 for this case. And what is X1? X1 is the Xt dash plus Xt transfer reactance plus X1 equivalent, because these two terms are same. So these two are in parallel. So the equivalent of this will be X1 divided by 2. Then this X1 will be our transfer reactance, so equivalent reactance between these two voltage sources. Now here, if we look here closely, all the reactances values are given. The magnitude of the infinite bus voltage is also given, but we do not have the information of C prime. Right? Inside C prime, this is a phasor quantity, so we have the magnitude of E prime as well as the associated angle. That is the angle delta, right? So first of all, we need to calculate this one so that we know the magnitude of E prime and also we can know the delta. And that delta will be actually the delta, the initial operating point. And after that, we will apply the formula. We will analyze the system. So that's why first we need to calculate this E prime. So the current across this network will be I. So using the KVL, we can write that E prime will be V plus X1, right? The voltage drop across this X1 plus this voltage. That means we need to calculate the I first. So what will be the I? We know that applied power, yes, will become V multiplied by the I conjugate. So what will be the I conjugate? It will be S over I. Now again, if you do the conjugation in both sides, then it will be I equal to S conjugate divided by V conjugate, right? Now what is S here? We have the PE and QE. So the S will be PE plus JQE, right? And here we need to take the conjugate of S. That means if we do the conjugate, only the sign of the imaginary part will change. So it was minus plus, now it will be minus. So E is 0.8, E is 0.8, and Q is 0.07. So it will be 0.8 minus J 0.07. Then the V conjugate, it is 1, is the magnitude, and angle is GTB. We can take minus sign here for the conjugation, but actually it doesn't. And finally, we will get this thing for then X1 is the equivalent reactance between these two terminals that we can calculate. It is actually 0.65 per unit. Then we can calculate this E prime. So we will V plus JX1I. If you put all these values, you will get this. Here, this is actually the magnitude of E prime, and this is actually the delta. And more specifically, this is actually the delta, right? The initial operating point. That's why look, the initial operating angle is delta naught, that is 26.387 degree. If you convert it into radian, it will be 0.46055 radian. Okay. Now we need to calculate the delta max. Okay. So how can we calculate? Now we need to understand some concept. Actually, we are targeting to calculate the critical clearing angle and critical clearing time. That means we need to consider about this case. So this is the case for 3-4 at 1 8, and this is for the calculation of critical clearing angle. That means we are at the limiting point. Okay. For this, actually, all of the available accelerating area has been used to dissipate the accelerating area of energy, right? That means this is our critical clearing angle. So here, whenever we is at the critical clearing angle, at that time the maximum swing, that is the F or the delta max, that actually counts across this PM line, right? Can you see it? This is on the PM line, right? But before that, look here, this is our fault clearing point. So we are not still at the critical clearing point, right? That's why the maximum swing, this is actually less than this case, right? And this F is here somewhere. why the power angle equation for before fault and after the fault will be same, and that will be this. It will be actually the P1 or actually the power before fault, or P3 the power equation after fault, that will be the same. It will be Pmax sin delta. So what will be the Pmax? It will be the magnitude of E prime, that is 1.17 here, and the magnitude of G, that is 1, that is given in the problem statement. And what is this? Divided by transfer reactance, that is x1, that is 0.651. So if you put all these values, you will get 1.8 sin delta. So this is actually the max Pmax in sin delta. So this is our power equation for before fault and after fault signal. And obviously during the fault, Pe2 will be exactly zero. So since the fault is at the beginning of the line, okay, here or here, the power transfer during the fault is actually zero. So we can calculate the critical clearing angle using this equation. This is now cos delta C. So now we know this delta max, we know the value of delta naught. So this and this are given to us. Also, we know this value. And what is P3 max? This is the maximum power in the after fault signal. So this is actually this 1.8. Okay. And what is Pm? We haven't calculated this Pm. So how can we calculate? Look, this is the Pm line, right? So you can take this point, this point. In this point, the Pm is P. P is here. It is actually the Pmax sin delta naught, right? We know this value delta naught, and we know the Pmax is 1.8. So we can calculate. So this is Pm. We can calculate this Pm. Then we can put it here. Finally, we get this. If you want to calculate the delta C, it will be cos inverse of this value. That will give us the 84.775. 84.775. So P3 max means, okay, this equation is actually the power angle equation for before fault and after fault. The same thing. So this Pmax is the Pmax for before fault as well as the after fault. And so this is actually the P1 max, or the maximum power for scenario 1, that is the before fault, or P3 max, the same thing, right? Now the critical clearing time is C. So this is the formula. It is due to the H. H is the inertial constant. That value is given. Then delta C minus delta naught. So what is delta C? We have just calculated. And delta naught is the initial operating point. We know this value. And then pi F naught is 60 hertz, and Pm is the calculation using this expression. Then we will get that our critical clearing time is 0.26 seconds. Now we will observe the swing curves for different viewing times. So before that, let me refresh your memory just by discussing this thing again. Actually, what was the journey here? Okay, what was the journey? point, now our fault is cleared out. So whenever the fault will be clearing out, the system will go into the after fault state. In the after fault state, it will be aligned with the before fault power regulator. That's why this point C will jump to point E, right? And before that, we have covered some accelerating area. This is our accelerating area A1. Then we are at E. Now here our PE is higher than PM, so there will be some deceleration and omega will decrease. But omega in the previous cycle omega increased, and now let's say omega has a very higher. So whenever omega starts to decrease, still this omega minus omega naught difference will be positive. That's why omega will decrease, but still the delta will increase. That's why we will go to the right side and we will come up to point F. That is our maximum slope. We will come to point F such that this area, that is area A2, can be equal to the area A1. Whenever we will be at F, at that time the omega will be omega 2. But here again the P is higher than Pm, so the deceleration will continue and omega will continue to decrease. And now this omega value will fall under this value. That means this difference will be now negative. Means that now the delta will decrease, right? That means now the journey will be from F to E, from F to E. So now what will happen after this journey? Now let's say we are at F. Now the journey will be from F to E. Then after E, it will follow this curve, right? It will not come like this because we are now at the after fault signal. So it will come here, it will come to this point.
Now, whenever the journey will be from F to E, so then from this E, the journey will still continue following this curvature, right? The horizontal curve, and it will come to this point. negative side. Let's say now let's say this area is equal to this area. That means it will go up to this point. This point where actually the PE and delta both are negative. Now again from this point it will come to point A. That means this amount of accelerating area will be 8. That area will be again balanced by this decelerating area whenever the point will come here. Then from F to A, then A to, let's say this is A, then A to A, then A to A. Like this oscillation will be continuing, right? If we do not actually incorporate any damping, then there will be sustained oscillation. So in this cycle, this point will come from F to H and again go back to the H. So this oscillation will neither decay nor increase for that time. It will be the sustained oscillation. But if we actually incorporate the damping, then the damping power PD will come into effect. And what will happen? This F will come to A, and instead of going to the H, it will go, let's say, a bit below point and then H. Okay. Then again, whenever it will go to this F, it will not reach this F, rather it will reach there. Okay. That means the oscillation will decay over the time. For the cycles, the oscillation will be decay. And then in the next cycle, it will come here. Then in the next cycle, it will go here. Okay. Like this way, at this point, the system will be stable. The system will be stable at point A, this point, right? So we will actually see the simulation or having animation of this thing. Okay. So that is some video to actually for the animation or simulation of this thing. That without damping effect and with damping effect. But have you understood what will happen for the without damping and with damping effect? Now let's go to this. This is the delta versus time response. This is also delta versus time response. Delta versus time. So now look, this is our delta, the initial operating point, delta now. Let's say this is 26.387. That we have solved. Okay. 26.387. Now, up to this point, there was no fault, right? The system was in the steady state. Let's say this is 0.1 second. So we have applied the fault after 0.1 second. So before 0.1 second, it was at delta. Okay, that value was fixed. But whenever the fault has been applied, then the delta value starts to increase, right? Because previously it was delta naught, now it will increase like this. Okay? Then it will go here, then it will increase, let's up to this, like this. So this is the critical nearing point. It's better if you look at this diagram. This. Let's say. So first it was delta naught. Whenever we applied the fault, this delta increased and it was increased up to this point. And the highest value of delta was the maximum swing, right? And in between this delta naught and delta max, we had the delta 1. So let's say this is here. So this is our delta naught. So after applying the fault, this delta starts to increase, and this is our delta max. Okay, and somewhere in between these two, there will be delta 1. Okay, not exactly between these two. It will depend on the PM line. Okay, because look, this delta 1 is not exactly at the middle of this delta naught and delta max, right? Because we have to make this area and this area equal. Then we have to look for where we can put this delta 1. Okay, it doesn't mean that always this will be exactly at the middle of this one. Because it will depend on this PM curve. If the PM curve is here, then maybe this will be our accelerating area, and to get the accelerating area, then we need to go up to this point. At that time, this will be the delta max, right? But always this delta will be in between this delta naught operating point, it is coming to point A, or the initial operating point. Okay. And due to this journey, there is some deceleration energy stored in the system. And to give it back, it will actually cross the A point, and it will go below. Okay. And it can go up to minus depending on the stored energy here in the deceleration area. If the area in the deceleration phase is higher, to compensate that, the point can go below the P equals to 0. Okay. So this is coming here, where actually this rotor angle is blue, this is minus, let's say minus 50 degree. Okay. This is the case. Then in the next cycle again it will go up to point F, and it will come to this point, let's say this is the same point. Then again it will come to F, then it will come to S. This will be the without S. This oscillation is sustained oscillation. It will swing in between these two fixed values. Okay. And this case is for the clearing time, we have taken 0.15 seconds. And what is our critical clearing time? That is 0.26 seconds. So we are still below than the critical clearing time. So this is, we are in the same position, right? Now in the next case, whenever we increase the fault clearing time, let's say from 0.15 to 0.2 seconds, but still it is lower than the critical clearing time, so the system will be stable. The system will not actually go to the unstable region. But what will be the difference? Look here, for the lower amount of fault clearing time, we get this delta max as, let's say this is 65. But now for higher amount of fault clearing time, we are getting delta max as, let's say 90. So actually this delta max is increasing with the fault clearing time. Why? You can easily sense that. Okay. Let's say the fault clearing time, then we are coming up to this point F, and this is our delta max, right? If we delay the fault clearing, then the C will be here, right? And what will be the accelerating area? This. And to balance that, this M should move in the right side, right? So it will be like this to balance this area. Now look, the delta max has been increased from the previous case, right? That's why whenever we will increase the fault clearing time, this delta max, the maximum should also increase. So that's why this has increased. But again, as this is below, then this 0.26, that is the critical clearing time. So the system will be stable, and for the without damping effect, it will be a sustained oscillation between these two fixed values. Okay. Now in this case, we have increased the fault clearing time from 0.2 second to 0.259. That means we are still below this point, that is 0.269. So the system will be still in the stable state, but obviously you can see a larger delta max because the fault clearing time is large. Okay. Have you understood this thing? Now let's try to see the simulation for without damping effect, and this simulation has been done for 2 seconds. Okay. So this is our green circle line that will give us the trajectory of the rotor movement. So this is the PM line. This line, this horizontal line is the PM line. This is the initial operating point A. Okay. And this is the P equals to 0 line. Look, this is the P equals to 0 line. This y-axis is the P, and this is the delta. X-axis is the delta. And this is a part of our power angle, not the whole picture, but just a zoomed version of a part. Because we want to observe the phenomena only in this side. Okay? Because let's think about this case. Here the rotor movement will only be limited to this region, right? From let's say A to B, then B to C, then C to E, E to F, then maybe F to A, and maybe F to this point X, right? Then again H to F, F to X like this. So only this portion we want to observe. Okay. Okay. So what we will see that, let's say we will start the simulation from t equals to 0 second, and we will apply the fault at 0.1 second. Okay. That means before this point 1 second, the point will remain here, right? Because there is no fault. So this is actually the delta values. It will remain here. Okay. Then whenever we will apply the fault, it will go to the during fault stage. That means the P will be 0. That's why this circuit will jump to here. Okay. Then we have assumed the fault clearing time as 0.2 second. That means from 0.1 second to 0.26 second, it will be in the during fault region, and over the time this delta will increase, right? This delta will increase and it will come to this point at t equals to 0.26 second. Now the fault is cleared out, so what will happen? This circle will jump to this, right? Now we are in the after fault region. Then from here the journey will be in this side and we will come here, so that this accelerating area can be balanced by this decelerating area. Okay. Then from this point again we will move backward and we will come here. That means from here to here again we are gaining this amount of decelerating energy that should be given back in the accelerating phase. That's why we will go here, and whenever we will go up to this p equals to 0 line, this area is not enough. That's why we need to this area is not enough. That's why we need to come up to this point, so that this area can be balanced by this area. Okay. And as this is the without damping effect, so in the next cycle we will see that again the trajectory will be from this line to this. Then in the next cycle again from this to this. So it will maintain these 2 points. It will make a decay output. Okay. Now we will run the simulation, then you will understand. Okay. Here we will see the elapsed time. Okay. Here we will see that the time. Whenever the time will be 0.1 second, you will see a jump from this to this. Still it is initially operating point. Now look, the jump is here. Now with the time, this delta is increasing. Okay, and our fault clearing time is 0.26 seconds. That means whenever this T will be 0.26, again there will be a jump from this place. Okay, look. Now here we have gained some accelerating energy, so we have to keep back it to this side. For that we have to come up to this point, and then from this point again the journey will be in the backward side. So again the green circle is going backward, right? Then we will follow this curve and it will come here. Okay, to balance this side, and from here we will again side. That means again it will come exactly to that point. Okay. Exactly to that point. Then again it will come. Okay. And this simulation is for t equals to 2 seconds. If you increase the simulation time, let's say 5 seconds per second, you will see this phenomenon forever. Okay. Whatever the simulation time, you will get the same thing again and again. Now, any confusion up to now? Let me discuss about the next case. Now, let's think about the weak damping scenario. Reduce the gap between and at some moment it will completely reduce this gap, and the PM and P will be equal, and the we want to include the damping effect. So this is the same thing. The fault clearing time is 0.15 second. Now with the damping effect, look at the maximum swing. This is 60 degree, but previously it was 65 degree, right? So it has already reduced in the first half cycle. Then in the next half cycle also it will be decreased here. And then if you continue the simulation, then maybe after 5 seconds you will see that we are getting a fixed point, we are getting a stable point, and that point will be at delta. Okay, for this case, because in this case, look, which is our final equilibrium point. Final equilibrium point will be this, right? Point A. That is the delta, the initial operator. That's why the final value of the delta will be delta. Now, if we increase the fault clearing time, so now this is increasing the maximum. For the without damping case, for 0.2 second it was 90 degree, but now look, it is below 80 degree. So it has increased. So again it will be this to this delta. Again, if you take 0.26 second, it will be still stable, right? Okay. Now an interesting thing. What is the fault clearing time here? 0.309. That is obviously higher than your critical clearing time. That was 0.26 seconds, right? But still it is stable. Can you say why? Because this fault clearing time is 0.309 seconds. Yeah. But if we calculated that our critical clearing time is 0.26 seconds. We are actually exceeding this time, but still the system is in the stable state. The answer is that actually we calculated this thing considering there is no damping. If there is damping, obviously the critical clearing time will increase. But obviously there should be some limit, because this we can't increase it forever, and we will not expect that okay, if we increase it forever, the system will stay up stable. That's not like that. Obviously, again, considering the damping, we need to calculate the DC, and for that we will get some new value of DC. Maybe that value of DC is higher than this 0.309. That's why in this value we are getting the stable operation. Okay, that is the case.
So there was excess acceleration, but still it was mitigated by the damping.
Yeah, exactly. By the damping power. The damping power will play that. So now, if we see again another simulation for with damping, what we will see? Again here the fault will be applied at 0.1 second. So before 0.1 second, the green circle will remain here, and whenever the fault is applied, it will come to this point, right? Then let's say fault clearing time is 0.26 second. So up to 0.26 second, this delta will increase and it will come to this point. Then it will jump to this, right? Then in the next journey, it will come up to where? Here, right? Look, this is the area A1, but here, let's say this is area A2. So this area A1 is higher than area A2. Why? Because the difference is actually balanced by the damping power. Okay. So it will come up to this point, then it will come to this point. That means it is gaining this deceleration energy. Then in the opposite direction, it will come up here. Then in the next cycle, it will not reach here, rather it will reach next second. Then in the next half cycle, it will reach here, right? Then here, like this way, it will be stable at this point. That will be the case. Okay? Have you understood this thing? Now let me run the simulation. You will see the difference. Whenever the time is 0.1 second, at that time the fault will be applied. Before that, the green come here.